The impact factor of the type of radiation is important. So, regarding the effective dose, radiation can affect organs. For example, it can impact the brain, it can impact the skin, and it can impact different organs. Each organ has different sensitivity. So they decided to use a unit called sievert. In particular, the way in which the distortion is allocated plays a crucial role in the overall process. This allocation is not just a random distribution, but a carefully calculated measure that ensures optimal performance and efficiency. I have termed this calculated measure as the effective dose. The effective dose is significant because it determines the extent. In dosimetry calculations and dose rate calculations, it does not take into account the effective dose. Here, it talks about milligray per second or microgray per second as dose rates. The dose that is considered here is the type of dose, but not the effective dose. This could be the dose received, whether the organ was the thyroid, neck, chest, abdomen, pelvis, or whatever the organ is. The effective dose has a different calculation, which is why in our calculations we rely on the effective dose because it is a consideration. All right, let's go back to the image intensifier. Here, we should not forget the significant role of the grid in also scattering radiation. As we can see, this is cesium iodide, and the X-ray has been converted into light photons. After that, it produced electrons that, through a voltage of 25,000 volts, began to accelerate. The type of cesium antimony then covers the optical phosphor and gives me the optical phosphor, which is made of cadmium zinc sulfide. The light photons that are generated here encounter something called the optical system. What is the optical system or the optical lens system? It consists of two lenses. These lenses have properties that refract light, meaning the light that hits them is refracted at a certain angle. As we can see, it travels in this path from this focal point and it gets refracted in this way. When it refracts like this and starts to move in straight lines, it encounters another lens that redirects it back to its original position. So, what is this part? This is the part of the camera. The camera tube receives this signal and displays it on the screen. The optical lens system is connected to the image intensifier, which transmits every point you have inside the output phosphor to the other side from the camera's location. In the past, they used the electronic TV camera, and there is the CCD camera, which is the charge cable device camera, the latest technology. If you remember, all televisions had a part that contained the cathode, which would extend out from the back. There was a screen and a part that was a cathode tube, all of which was vacuum sealed. You would find the cathode coming out from behind. All the TVs were like that, until now. But this concept has faded and changed, and the mechanism is different now, and all the screens have changed. So, we are following a good sequence. I hope you understand. I'm just jumping a bit in the discussion, but I'm trying to keep things in order. Is everything clear, doctors? Or are there any issues?
Okay, doctor, I don't want to dismiss them all because everything is interconnected. And there is a question, doctor, regarding what happens when I reduce the field of view. You say that when I reduce the magnification in the output phosphor, what occurs? We reduce the brightness. Why do we reduce the brightness? Why is the brightness reduced? Because it gives us high resolution. All right, okay, I will connect it for you again, doctor.
Is our situation still the same, doctor? First, what is magnification gain? This is the basic understood image that was present at the input screen over this entire diameter. You will receive it in the end, and you will perform magnification onto this small part, right? Am I wrong? Stay with me, Dr. Honey. Is this magnification or not? This is magnification. The gain is the amount of reduction that happened here. If the diameter is large and you reduce this diameter to a small part at the bottom, that is the magnification itself. This magnification gain, okay, the light photon. All right then. The light photon that appears at the output phosphor, the ratio between it and the incident X-ray photon, is what I call flux gain. This means that within my X-ray system, it will show how many light photons will ultimately be produced. What do I call flux gain? I mean, when I enter an X-ray system, how many photons will it produce in the end? In the end, I had one X-ray with a phosphor input that produced 2000, then 3000. The more you reduce, the more you have your flux gain similar to that. So you have the efficiency of the X-ray emission, the efficiency of the phosphor tube, and the kinetic energy like the voltage. So we talked about the magnification gain and the flux gain. Now, when the number of magnification decreases, what does that mean? Like this, magnification means the exposed area is large, right? So if the magnification is large, does that mean the number of photons produced will be high or low? High. Will the number of electrons produced be high or low? High. Great. So when the number of electrons is high, there's a point at the phosphor input where 100 electrons entered, and then 1000. Which one do you think will give a higher brightness? Give me medium light intensity. So, in the case where the diameter is large, the light photon increased. So the number of electrons is more, and the brightness increased, right? So therefore, when your magnification gain is high, your brightness is also high. The efficiency of the number of photons that come out for the X-ray photon or for the X-ray photon itself increases as well, which also enhances the brightness. However, when I reduce the diameter, it means that there is a part of your field of view that you didn't take with you during the focusing process. You reduced the diameter, and there is a part that you didn't capture. So did the number decrease or increase? When the number decreases, will the brightness decrease or not? But since the spaces between the electrons decreased, every point became closer to another point. So does the resolution decrease or not? Now you are gathering 1000 electrons in a small village, but I will gather 100,000 electrons in the same village. Original understanding. At this point, you started from these spaces, you mentioned your area or the number of electrons. Yes, each electron gives you a signal, providing a signal next to it, while another electron brings another signal from a different location. So your resolution is high, but the number is still low, so you are receiving a signal. Yes, the brightness decreases, and then the automatic brightness control, which is the sensor here, starts to tell you to increase the programs to enhance the brightness that exists, so you have increased the dose on the brightness. Is that clear? And the image on the output phosphor is the inverse of the image on the input. It appears inverted here. So who adjusts it? Who adjusts it?
The image that appears, please, I mean the arrow you have here is pointing, and then what was above is now below, and what was below is now above. The output image has become inverted compared to the input. So how is it corrected later? Well, this is the camera's job, and it's quite simple. You have the image, and you know it's coming to you. Right, doctor?
Okay, you received it inverted. Is there any missing data? No. No. Is there a problem today when we adjust the image? You know that the data you received is mixed up. Is there a problem when the image is being adjusted? No, there is no problem. Just fine. But the image that appears in your photos is turned upside down. I know that the signal coming will reflect this in the display, nothing more than that, and nothing less. The values in the conversion factor, flux, and magnification, these values are roughly speaking. The magnification here is 100, the flux is 100, and the conversion factor is, for example, 10 or 30 or so. To be honest, I found many books with different values in various contexts. I can't tell you to memorize these numbers, but at least know the range that these numbers can fall into and situations. However, I found other books that talk about different numbers for these matters, so I think it is contingent upon the specific type of machine itself. This is a miniature of the part that you will take, or the part that you will take from the phosphorus input. So, what will happen is automatic brightness control. In order to achieve this, for example, this image is during the magnification, and this increases the magnification. So what will it do? It will tell you that I now want to increase the dose, the trans dose that is entering the patient, to enhance the level of brightness that is present here, for example. The image intense fire exposure rate is about 30 microrontgen, which represents the exposure. We mentioned that the first term is exposure and the second term is also exposure. If your exposure rate is 30 microrontgen per second, this is for a 25 centimeter mode, meaning you set your dimension or field view to 25 centimeters. Does that mean you perhaps keep your thing or your thing? Okay, 60 microrontgen per second for 17. Did you notice what happens? Your dose or exposure rate increases as you reduce or change your field view or field size. You increase the dose rate that your patient received. And at 12 centimeters, it reached 120 microrontgen per second. This is the same idea in the case of normal and in the case of magnification. In fact, here, for example, you get a higher resolution. That's it. Here, the same idea applies. Increasing the magnification results in higher resolution. Also, the same concept applies to achieving the same level of brightness. You need to increase the dose for the patient here. Dawood in Zaman Balin Maknafsh is important. I will work a lot because I am turning many Palestinians upside down. Forgive me on this matter, but I like to explain in a way that is different from the existing word. The image intensifier has problems. What are the problems it faces? Why do they occur? I currently have my field of view or my input phosphor large like this, right? And my output phosphor is small. So, isn't it possible for a light photon to experience scattering? It was mentioned that there is an X-ray photon entering here, and it does not follow the same path and sequence that I am following. It was also mentioned that there is an electron that gets scattered from my field and also travels to the output phosphor. Well, this will not just create an artifact. It will create an artifact The artifact called Villing glare reduces the contrast in the image. You have an image here taken with the image intensifier and another taken with the flat panel detector or digital system. The scattered radiation, scattered electrons, or even the light photons that form at the output phosphor can also scatter back and may interact with the photocathode, becoming photoelectrons and affecting the signal that reaches the output phosphor. All of this reduces the contrast of the image, as we can see here. With the vessels or coronary arteries that are visible, they have less contrast than the coronary arteries taken with the flat panel detector. That's why the digital system avoids the problems that appear with the image intensifier, such as viewing glare and distortion. The visioning artifact, as we will discuss now, is the effect of the scattered radiation. That's why they tell you that we put aluminum on the output phosphor here to absorb any returning scattered light photons. This starts to create absorption, but this does not prevent it from happening. There is also an artifact known as the visioning artifact, which occurs when using the input phosphor or when the field of view becomes large. This results in an uneven collection of light photons, meaning that some are concentrated in the peripheral area of the field of view, while others are in the center. As a result of having a large field of view, the collected signals that eventually reach the output phosphor may be influenced by the presence of peripheral X-ray photons coming from the peripheral field of view. Light photons will appear on the output phosphor, and the electrons may also be affected by uneven collection in the center of my field of view at the periphery. Why is this? It is due to the concave shape of my input phosphor, and the inequality in it will make the electrons present at the periphery fewer than those in the central area. This will result in the electrons at the periphery being less focused than the electrons at the center. Therefore, the electrons you have at the center will always be more focused than the electrons present at the field of view. This works with generating artifacts, which means that you feel there is an image here. I brought a disc, like a disc made of lead, and I took a picture of it. If you now bring a metallic object and place it under the X-ray tube, this part should appear white on the film, not black. Why did the white turn black here? Don't let the defect that appeared here be black. Why, doctor? Why is the background here white and the part that is the LED appears black? Is this an image negative? Image negative or image negative or image negative? Is this good? Well, it starts by taking something called, are you thinking about the line profile topic? I take a line and start seeing the intensity in each pixel. What is its value? The line profile that I have here will notice that in the area of the LED disc, the value has decreased significantly. This is normal. Why? Because your interest here is actually low due to the presence of the LED disc, which is causing radiation absorption. But this area should be high because nothing should cause a loss of signal in this periphery area. However, it was found that there is a drop. This drop is due to the fact that the electrons in your field are still focused away from the center, which will cause a loss in the brightness present. All right, doctors? Yes, that's right. So we have talked about and discussed. Let's talk about the topic of curvature. It has many problems among its issues. It helps with the topic of focusing. But what are the problems? If we capture this grid, it means something has high materials. And if I take pictures of it this way, there is a significant observation and a minor observation. You find that in the case of the minor observation, your image shows homogeneity in the periphery and center like this, while in the large field of view, it seems that the area of the periphery at the edges was stretched, as if someone was holding it and stretching it from the edges, right. So, what happened here is due to what? Or as a result of what? The punction artifact or distortion. That's it. As a result of having some of the electrons present in that periphery area, particularly in the outermost region, they will concentrate at a location that is significantly further away than what is typically observed, than the focusing that occurs in the normal beam. Therefore, in this particular scenario, the phenomenon that will occur is that the part that is elongated or extended in appearance, or the part you have in the periphery, will appear in this way, as though the visual representation has manifested in this manner. Upon careful observation, we can discern whether this image is inverted or remains in its normal orientation. An inverted image indicates that this part, which is in the peripheral vision area, is significantly influenced by the expansive large field of view. Consequently, as a result of these occurrences, or due to the large curvature, the intensity level that is reached is notably different from the intensity that is supposed to actually reach the central point or my field of view. This phenomenon is the primary cause of what is known as the punction artifact that exists. Currently, if there happens to be a strong magnetic field affecting the area near the vicinity of the image intensifier, there are electrons present, and these electrons, which are in motion, are being carefully focused. It itself generates a magnetic field. Well, if there is a magnetic field once, a magnetic field has been exposed to the image intensifier. This magnetic field can be generated by computer systems, for example, or by devices around the image intensifier. Anything that conducts electricity will have a magnetic field. Remember how we used to place our mobile phones next to our laptops and say that someone might call us because there were strains in the magnetic field and we started to hear interference? Any device that conducts electricity has a magnetic field. Now, this magnetic field will affect the movement of electrons. The movement of these electrons will take the shape of an S-shaped distortion artifact. The S-shaped distortion artifact means that the signal reaching the phosphor is distorted due to the movement of the electrons. Instead of appearing as straight lines, the signal will take on an S shape due to changes in its path or trajectory as it moves. Of course, this topic requires the image intensifier as well. For example, if someone has a machine, whether it's an X-ray machine or a fluoroscopy machine that has an image intensifier, they must ensure that there are no external sources affecting the area being examined. It can affect, for example, the nearby units, so there must be a specific magnetic field. All of this needs to be considered in the planning or in the design of the machine itself from the beginning. Isn't it normal, doctors? Now let's talk about some things before we get into the topic of the video. There was a question from one of the doctors asking about filters, specifically the high pass filter and low pass filter, right? There was a question like that. I always tell you that you have a low pass filter, a high pass filter, and sometimes I tell you about a band pass filter. My image, which receives the signal, is affected by these filters. Do you remember when I mentioned the line profile? When we say that if you take a line profile like this, it will start to appear in this way. Okay? If I increase the number of line pairs significantly in a small distance, then the frequency of the wave will increase. So I named the first type of noise as low frequency and the second type as high frequency. All right? The noise that exists in the image, any noise present in any image in the world, appears in what way? It appears as if